From the outset of Western thought, thinkers have argued about whether the world is fundamentally static or in flux. This is no mere philosophical debate. The extraordinary success of science is founded on the notion that unchanging laws, universal laws, underlie everything. Yet now, based on the investigation of ancient quasar light and the X-ray properties of distant galaxies, leading scientists are challenging this central idea and proposing that the very laws of the universe might change. Are unchanging laws the only way to understand the universe, or do we need a radically new framework to make sense of a universe in flux? And if we were to accept changing universal laws, would we not require unchanging laws that explain those changes themselves? Well, now to our speakers. Lee Smolin, on the screen here, is a revolutionary theoretical physicist. He received his PhD from Harvard in 1979 and has since authored several books, including Einstein's Unfinished Revolution, Time Reborn, and The Trouble with Physics. Sabine Hossenfelder is a theoretical physicist who specializes in the foundations of physics. She's a research fellow at the Frankfurt Institute for Advanced Studies, where she leads the Superfluid Dark Matter group. Sabine is also the author of Lost in Math: How Beauty Leads Physics Astray, which explores the concept of elegance in fundamental physics and cosmology. Paul Davies is a world-renowned physicist and best-selling author. He works on the big questions of existence, ranging from the origin of the universe to the origin of life, and from the nature of time to the foundational questions in quantum mechanics. So we're going to begin I'm going to begin by asking the three speakers to address briefly their position on the central question that we're aiming to address here, and then we'll get into the more general discussion. So if I could ask you each to address this question: Are the laws that govern the universe fixed, or might they change over time? Paul, could we kick off with you?
But yes, and we're going to kick off by my pressing this. I'm limited 3 minutes. Might, I think, is correct. The notion of fixed laws actually is something of a hangover from theology, the foundation of physics 3.5 centuries ago. Doesn't mean that fixed laws are wrong, but it does mean that maybe the time has come for us to reevaluate whether fixed laws are the best way of organizing facts about the world, or are there other ways of organizing it? Could the laws of physics change with time? We're going to be discussing that, but I wanted to throw in two ways that is not normally discussed in that context. And the first of these is that the computational view of the universe, that nature is really performing a gigantic computation rather than infinitely precise, abstract, Platonic mathematical laws, that it's really more of a computation, raises the question about whether the computational resources of nature are limited, whether there are things like rounding errors involved. And what this would mean is not so much that the laws would change with time, but there'd be some flexibility or error or uncertainty in the laws, like we're used to in the case of quantum mechanics, uncertainty in the states. So that's one possibility, that maybe the laws don't so much change over time, but become sharper over time. The other is that I don't think fixed laws are a very good fit to biology. Biological systems undoubtedly are dynamic. There are patterns and regularities, but the concept of open-ended evolution is not something that really fits in well with the notion of fixed laws. The last thing I want to throw in is the possibility that the laws of physics might not so much change with time as change with the complexity of a system. And I've considered in some of my research the possibility of laws which become functions of the state of the system. So as the states change, in standard physics, laws are fixed, but the states of the world change with time. But if the laws are functions of the state, then that gives you pathways to complexity, which we simply haven't considered before, and I think that might be a better fit to biological systems. So, and the last point, I've got 30 seconds, is that when it comes to cosmology, the notion of a law is something a little peculiar, because a law by definition applies to a class of systems. And if there's only one universe, what does it mean to say that there is a law for that universe? Now, there may be more than one universe. We'll get into that a little bit later on. I've run out of time. I'm going to stop there.
Thank you, Paul. Brilliantly timed. Sabine.
So I think when we ask whether the laws of nature that govern the universe are fixed or change over time, we have to first ask what laws are we even talking about. So we do have some laws of nature that describe the universe. So that's quantum field theory and the standard model of particle physics and general relativity, and those don't change in time. So to that extent, I would say our best current description of the universe just doesn't have this property. Now, of course, one can generalize the theories that we currently use and ask whether it agrees with observations. So if we make them time dependent, what would be the observational consequences, and do we see any evidence for that? And to my best knowledge, the evidence is just no. So it just doesn't describe what we see. And also, I mean, this is a point which has been made very many times. If we would have a new law that is time dependent, that would also be a law, right? So there would have to be a law for that time dependence. So it's kind of a circular question. What do we even mean by a time dependent law? So this is why, for me, the more interesting question is whether the type of law that we currently use in the foundations is really the right one. So the laws that we currently use, they all work the same way. We do have a specification of an initial state at one particular time. That's basically all the information about the system that there is to be. Classical mechanics, it would be the momentum and position of the particles. And then we have what's called an evolution law that tells us if we feed in this initial state, we can calculate what happens at any later time. And it's an interesting question to ask, why do all the fundamental laws of nature have this form? And I think it's just because that's the way that we make experiments. We prepare something in an initial state, and then we observe it and see what happens. And then we're looking for an equation that describes what we observe. And I think that's why we're using these differential equations a lot. But that doesn't mean that this is fundamentally the best way to go about it. Which brings up the question, like, could it be that there are entirely different types of laws of a different form, not this kind of differential equation, that would actually be more useful to describe our observations?
Thank you. Lee, it's time to bring you in, and I'll just remind you of the question we're asked to address here. Are the laws that govern the universe fixed, or might they change over time?
Philip, I've been thinking about that question since the mid-1980s, so don't worry, I'm not going to forget it. It's a great honor to be here with my friends Sabine and Paul, who I've known for a long time and been discussing these things for a long time. My thought, and I will address the question of the meta law, is how could they not? How could they not? If we want to explain the laws, and I know that you each will come back with something, but I have new things to say, and let's get to the new things we have to say. I'll start with the thing I always say, which is to quote Charles Sanders Peirce, who said that when you explain a system by referencing the laws, that's not the end of the explanation. We must explain how the laws came to be and why there are these laws and not other laws. And he goes on to say, this is 1893, in the Architecture of Theories, that the only scientific explanation which could, in a scientific, that is testable manner, explain to us why these laws are not others is if the laws have a dynamical process of evolution. And I'll give you an example so that this is not something mysterious. It's an idea I invented called the principle of precedence. The idea is, well, first of all, why do we think that the laws don't change? Imagine we prepare a quantum system, we let it evolve, and then we do a measurement to find out which final state is emerging. And we can talk about quantum mechanics as well. If there is a time-independent law, that question to the universe generates some probability distributions. Sometimes if you start in state X, it goes to state up or to stay down with certain probability. We could reproduce that with a very simple, although silly-sounding law that simply says if you're a part of the universe, an atom or some system, and you're asking what happens next, look to the ensemble of past situations of the same specification and pick one randomly. And that will reproduce exactly all the complicated laws. Now you can say, oh, that's real, you're being really silly. How is a system, a quantum system, going to know what all of its precedents are? But there are equally silly questions we go right by all the time. Like, how does an electron know to obey the electron part of the standard model law and not the quark part or the neutrino part? So I am convinced that the way forward in physics is, first of all, and this took me years and years to get my head straight against. If we're going to talk about laws evolving, we have to talk about a universe where time is not only real, but dynamical and active, and in some sense creating the events as time goes on. And indeed, the creation of events is what time is.
Thank you. Yes, and Lee, I hope we'll have time to get more into some of those ideas later, because it's very hard to condense them into 3 minutes. But to kick off the discussion, I think we ought to sort of start with the basics and ask what even is a scientific law. I mean, scientists, talk a lot about laws. You might remember Hooke's law from school. Well, that can be broken. So, what is a law? It reminds me of the cartoon of a policeman hanging onto a guy who's floating up in the air and saying, "I'm arresting you for breaking the laws of physics." When can we break the laws, and when are they meant to be inviolable? So let's think about what is a law of physics. And Sabine, if we could start with you.
I always get the most difficult questions. You can look, for example, just at terminology, like what is it that physicists actually call a law? Like we have Hubble's law, Hooke's law, you already said this. So this makes me think what physicists call a law is any kind of regularity that we observe in nature and that we can formulate using mathematics. But there are also some things that I think should be called a law following this logic, but they are not. For example, Schrödinger's equation. Why is it not called Schrödinger's law? I have no idea. Or the Friedmann equations, it's the same thing. Why are they not called a law? So I don't know. Like if I had to write down a definition, I would say it's an observed regularity written down in mathematics.
Okay, thank you. Paul, what's your take on a law?
Well, it's true. It's a sort of sloppy definition. And when people ask for an example of a law, I think, well, what about Newton's law of gravitation, the inverse square law? If you're twice as far away, the gravitational pull is 1/4, and so on. Seems very easy. And I mean, it's correct as far as it goes, but it's subsumed within Einstein's general theory of relativity. It's more encompassing, better description of gravitation. It's an approximation in that theory. And then during my career, there's been this huge movement towards the unification of physics. So the laws you find in the textbooks on my bookshelf in my office are not the last word. And the hope is that there will be some sort of final inviolable super law, which would be a formula you wear on your T-shirt. And that would be it. That would be the ultimate law, and all the others are approximations to it. But Sabine is absolutely right. Why do we not have Schrödinger's law? And the one I like to quote the other way is Ohm's law applies to electric circuits. But was Ohm's law valid in the Big Bang or something? There were no electric circuits, and so the very concept of law. But I just want to throw in one point as I've got your attention. There's a law you learn at school. The law of conservation of electric charge, and it illustrates the point I was making earlier. What does that mean? What is a strict interpretation of the law of conservation of electric charge? It means an electric charge cannot change. And you think cannot change by a little bit, tiny little bit, teeny weeny little bit. The strict reading of that is it's an infinitely precise statement. So there's zero change. That's what you're supposed to believe. But that's completely untestable. There's no way that we can ever, infinity is an abstract concept. It's useful in mathematics and it makes calculations simpler, but we can never measure an infinity or a zero. And so making laws infinitely precise is an act of faith. And that's why I say perhaps we should consider sort of fuzzy laws, flexible laws, where the fuzziness might be a function of time.
Okay, and Lee, in coming to you, I wonder if we could zero in on the question, I think we've touched on it already, of perhaps there's a question here of what are the laws supposed to be governing? And I'm thinking in particular...
I'm with you. Let me jump into that.
Yeah, sure.
What Sabine was referring to, and Paul, when she said that the laws always have the same framework, that's what I call the Newtonian paradigm of the Newtonian framework. As Sabine said, fixed space of possible states, which is also the fixed state of possible initial conditions, and a time-independent dynamical law that moves them forward. In work with Roberto Mangabeira-Unger and a book of about 5 years ago, we explained, and this is really the crucial point, that such a law could only be applied meaningfully to a small subsystem of the universe. There are several reasons why that is. One of them is you test such a law's validity by starting out with different initial conditions and showing that the same evolution law indeed does govern in testable ways different initial conditions. And to have systems with many different initial conditions, of course, they have to be a small part of the universe. So that's what I understand. That's a kind of law, a law that governs a very small part of the universe. We're very good at that. We live in a small part of the universe. We look around, we see other small parts of the universe, like other galaxies and so forth, which seem to be obeying pretty much the same laws. But if we ask what kind of law selects those local laws, those laws of small regions, what kind of law governs the cosmological questions we want to ask, like what chose the laws and what chose the initial conditions, that must be a law of a very different kind. And it must have a different methodology and different formulation. And I can come back later and explain. But if we don't get that distinction between a law of a small part of the universe, which only makes sense if it's applied to many small subsystems, and differentiate that from hypotheses about the universe as a whole, we don't get started. So let's keep that distinction in mind.
Okay, thank you. Well, it's time to move on to the next theme that I want to explore, which is whether unchanging laws are actually necessary for understanding the universe, or whether we can embrace the notion that they change, and if they do, what is governing that change? But before we get into that, I wonder whether we ought to just spend a little time motivating why we're having this discussion at all. Why are people thinking that perhaps the laws that are thought to be fundamental might change? And Paul, I wonder if you could talk a little bit about what has motivated this challenging of the notion that there are these sort of fundamental unchanging laws.
You mentioned about the quasar light, and are you referring there to the work of John Webb, which I can say something about, about the possibility of fine structure.
Yes, exactly. You see, which is a slightly different thing perhaps, because there it's talking about whether the fundamental constants are changing or not.
But that's still part of the law-like nature.
So it would be nice to think about that distinction, or if it exists. So yes, if you can say.
So let me just deal with that first, because it's a contentious issue, but it illustrates the sort of difficulty. Part of the panoply of the laws of physics are that there are certain parameters. These are numbers which you have to measure. We don't know why they are what they are, but my favorite is called the fine structure constant, and it's made up by combining the charge on the electron, Planck's constant, and the speed of light, and it has the number, it comes out to be a pure number, 1/137, nearly, it's not exact. And so if the aliens are out there measuring these things, doesn't matter whether they've got base 20 arithmetic or anything of that sort, they'll come up with the same number, basically, the same number. And so there's a universal constant. We can't derive that number from any known physics. I've spent a lot of my career thinking how we might be able to do that, but nobody's done it, so we don't know why it is what it is, but it's supposed to be fixed. And then a few years ago, astronomical evidence, some of it collected by my old friend John Webb, at that time at the University of New South Wales in Sydney, he looked at the spectra of quasars. So these are compact, highly luminous objects, sort of right out there. So we're looking back at billions of years ago. And so we're seeing physics as it was billions of years ago. And there's a slight hint, not much more than that there's been a change in that number, that 1/137 almost, has changed very slightly. Maybe a little sort of glitch in that number. Very contentious, but if it were correct, if it was confirmed, then it would show that the laws of electromagnetism and or quantum mechanics, something is shifting there or had shifted. Maybe you don't have to have a sort of continuous shift. It can be a glitch, it can be a sudden thing, it may be a function of the universe in some way. We don't know, and it may all go away. But it relates to exactly the point I made earlier, because the law of conservation of electric charge is also the law of conservation of that number if you fix the speed of light and Planck's constant of quantum mechanics. So if that were to change, it's an example of the lack of precision when you say exactly fixed electric charge. Your question, though, Philip, was why are we thinking about these things? And for me, I've always thought about it in connection with cosmology, because as I said earlier, there's only one universe. Maybe it's got different rules from everything else. But for me, I've got really interested in biological systems and whether there's new physics lurking in living matter. And when you try to apply fixed laws of physics to living matter, it's just not a good fit. It's not a good way of approaching. It doesn't mean those laws are broken, but they're just not very useful. And that what we really need is a new conceptual framework for dealing with those systems, particularly with the open-ended evolution, as I said earlier. So that's why I'm thinking about these things at this particular time.
Okay, thank you. Sabine, I had the sense from what you said initially that you maybe feel that there are some laws, as far as we know them at the moment, that aren't up for grabs, that are going to be fundamental, perhaps general relativity as one of those. Is that your position? Do you feel that there must be unchanging laws that are governing the universe somehow?
No, I don't think so. I think I'm fairly open-minded. Whatever works, works. So the question was, are unchanging laws necessary for us to describe the universe? I don't know, but they're certainly useful. We know this already. So, for example, this evidence that Paul was just talking about with the quasars, I'm not terribly excited about it. It's cool that they are making these observations and all of that, but in cosmology there are so many tensions, between observations that don't really fit into the current paradigm. That makes me think we're close to seeing a major reorganization of this whole framework, and God knows what happens with this particular thing. Maybe it may just go away with a reanalysis of the data. So I have two reasons to think about different types of laws. One of which is what Lee already said. So if we look at the universe as a whole and we're trying to understand where it came from, then really the laws that we currently use, general relativity and quantum field theory, it doesn't really help us all that much, because they always need this initial state, right? And then you can always ask, well, where did this initial state come from? Well, it came from an even earlier state, and where did this come from? So it becomes this chicken and egg problem. And to really solve this problem, you need an entirely different type of law. For example, the kind of law that Lee was talking about that evolves. But the other reason I've been thinking about it comes from quantum mechanics, and I'll take 2 minutes to try to explain why this intrigues me. So in quantum mechanics, we have a lot of observations of weird experiments that you've probably heard about. People always say quantum mechanics is strange and you can't understand it. It's something with Schrödinger's cat and that kind of thing. But if it's it's quite easy, at least I find it easy, to make sense of all this supposed quantum weirdness if you allow the state in the future to play a role for the evolution of the system. And I know a lot of people think I'm really, really crazy for saying something like this, but if you think of something like the double slit experiment, where you're preparing your initial state, say it's a beam of electrons, and it hits the two slits, and it creates an interference pattern. Okay, so fine, you would say, so single electrons can interfere with themselves, okay. But then, when you try to find out which slit did the electron go through, the interference pattern vanishes. And why is that? It kind of seems like the electron knows what's going to happen. And you can actually choose what you measure after the electron has already left your gas, whatever. So how can this be? And if you allow the evolution of this electron beam to depend on what will be measured, suddenly it all makes sense. But you can't describe a time evolution like this using the laws that we currently have. So for me, this is the other reason to take this seriously.
Lee, I think this would be a good time if you can say a little more about the idea that you've proposed, which is that, if I'm going to put it too crudely, forgive me, but that it is conceivable that laws have emerged from lawlessness, that they are emergent properties, and that precedence has something to do with that. Can you explain that position?
Well, I think I did, and I'd like to take that and go a little bit further in the direction I was going. You'll see that it fits together. And thanks to Sabine for agreeing. It's very unusual to have some agreement with you. That's beautiful. One of the things that I've been thinking about when I think about what a law on a cosmological scale must do is I reached the opposite conclusion of many of our colleagues. And it was really Roger Penrose who first said this to me, that we should seek as much asymmetry, as much difference as possible as we go down to smaller and smaller scales. So with Julian Barber, we invented a measure of the difference of the viewpoints of the events in the universe. And we call this variety. And it's a kind of measure of complexity, but particularly it focuses on comparing the views to the past that different events have. And it's a long story, but to make it very, very short, I found that I could derive Schrodinger's equation, or Schrodinger's law, if you like, under the right circumstances, from a posited law that the universe makes sure that there's as much variety as possible, which means the view from any two events can be differentiated. So that's an example of a new kind of law that has to be applied to the universe as a whole. And it has as a consequence Schrodinger's equation in a certain limit. And what's beautiful about it is it also has as a consequence the corrections to Schrodinger's equation. If we imagine expanding in the inverse of the square root of the number of particles in a quantum system. And that may be testable, and that I'm very excited about.
Okay, well, thank you. I want us to talk now about the question of, if ideas like this prove to be the case, or if observations showed that actually things do seem to have changed over time, the laws or fundamental constants, what would that imply? And I'm thinking, for example, that there is this idea at the moment that we can seek to understand the very early stages of the universe by looking experimentally at things that we can recreate through particle collisions or however now. But if different laws applied back then, that challenges that way of doing science. So I wonder, and Lee, if you could begin by talking a bit about this. If it turns out to be the case, if you're right, or if even it's a possibility we should entertain that laws are not fixed, that they are changing and have changed, what does that imply for scientific practice and for the way we think about science today?
I think it implies that we must, as Sabine said, and Paul said, quite radically change our view. And one of the things I think is that we have to get serious about Heisenberg, and particularly get serious about Heisenberg and Bragg and Freeman Dyson and many people who said that embedded in the quantum description is the difference between the present and the future and the past. And this is something that takes a long time to get useful, because it's not how we're used to thinking, that quantum mechanics is built into the flow of time, the flow of moments, and treats the future, the present, and the past differently. And in work with Clelio Verde, we've been investigating some pretty radical versions of this, in which there is no past, there is no future, there is simply a present moment made up of events that continually create each other. So the picture we have of the world as something that exists deeply in time, and we have to explain why the laws a long time ago were the same as the laws now, goes away. And the question that we have to understand in the work we're doing with Verde is how the universe persists, why the universe as it's recreated moment by moment is similar to the universe that was a few minutes ago.
Well, Paul, I wonder if I could open that up to you. In particular, if that is the case, I mean, if ideas like this prove to be the case, it sounds pretty destabilizing for our sense of science as it has traditionally been, of a search for universal truths and perhaps for kind of eternal truths. But is that what science should be looking for?
Oh, most of them don't. The sort of people I have coffee with do, but that's a subset. And what Lee is saying is of such enormous interest to me that I'm not going to go there, because otherwise we'll never get out of this tent. Because all this business about the nature and flow of time is dear to my heart. What I wanted to do was to say, in addition to, are the laws flexible or changing with time or not a good way of organizing our data, is to throw in new kinds of laws. And there's a couple that I should mention, because it really goes into this whole discussion. The law, I don't know how much physics here people know, but it's been said a couple of times this morning that the laws are only part of it. If you want to throw a ball in the air, you've got a sort of law of the parabola, that's fine, but you won't know which parabola unless you specify the initial conditions, the angle and the speed of throwing it. And that's true of all of the dynamical laws. And Sabine was mentioning differential equations, and that you have to have initial conditions for those. So come to the universe, what were the initial conditions of the universe? The Big Bang was remarkably uniform. Why was that? Well, we don't really know. And so you sort of assume that alongside the laws, say, like of gravitation, that might apply to the universe, you then have to specify the initial conditions. But many years ago, Jim Hartle and Stephen Hawking came up with a proposal, which was, I won't go into it in detail, but it was effectively a law of initial conditions. So you've got all the laws of physics, we don't know where they come from, or why they have the form that they do, and whether they change with time, that's the other thing. So it's all a mystery. Why not throw in a law of initial conditions as well? Don't know where it comes from, but you posit. That is maybe a law of initial simplicity. And so they had a particular proposal. It was motivated by quantum mechanics. Don't need to get into it, but should we consider that, particularly in cosmology, a law of initial conditions as well as dynamics of the universe? And there's another example of a law that it's not scientifically respectable, but it was cooked up between Wolfgang Pauli, the physicist, and Jung, the psychologist, psychoanalyst, and it was an a-causal connecting principle. It was called synchronicity, and people often refer to this if there are coincidences, and it's usual in science to say these coincidences are just coincidences. It's not anything deeper. But imagine we've got a space-time as a big map, time this way, space that way, and we've got all these events, and our laws govern what happens as the universe evolves, as we've been discussing, and it's limited by the speed of light. So what happens over there and what happens here can only affect each other causally if light has time to go between them. But what if there's a law outside of that? It would lead to strange patterns in space-time which would not be captured by those laws. We can't rule that out. That what happens here might depend on something that happens, as Sabine was saying, in the future over there. You can't rule those out, those sorts of patterns. So this is just enlarging what we might consider if we're going to put all of this in the melting pot. I'm not suggesting any of this is actually correct, but we must be open to it.
Well, I think what's striking in recent years is how, quite aside from whether the laws that we observe are unchanging or not, it seems to be a bit more respectable, let's say at least, to suggest that there may be other universes that have entirely different laws, that our laws may not be at least unique. And Sabine, I wonder if you could comment on whether you find that a useful thing to suppose, given how difficult it is to prove or disprove or investigate.
Well, so I was about to answer the question, but now you ask a different question. So about the multiverse, I mean, is it useful? I mean, I would say to some extent it's useful as a kind of thought experiment. Like we can write down different laws and we can ask, well, what would a universe look like? That was a little bit different. What would happen? Is it useful to actually describe the observations in our universe? I would say no. So from a scientific perspective, to explain observations, I don't think so. But it does have some use, say, to get to know our theories better. I would acknowledge this. But if I may,
yes, please do.
I would like to add a point to the question: what difference would it make? Like, what could we learn from it if we develop new laws? And one point Paul already said is that we may have this weird influence from the future or from very different parts of the universe, actually, which I totally understand. People think it's crazy, but it might actually help to explain some things that we observe, for example, the measurement process in quantum mechanics, but also, and this is something which David Deutsch has been working on, and I also put Lee's cosmological natural selection in that area. It might turn out that we're wrong to look for more fundamental laws by way of reductionism, ontological reductionism, looking at shorter and shorter distance scale, which is kind of this route that's driven by building bigger and bigger colliders. Because it may be, to use this example from cosmological natural selection, that the laws come about by optimizing a particular macroscopic property. And in Lee's theory, that's the number of black holes in the universe, it's not a fundamental thing. Black holes are not elementary particles, but it's definitely a well-defined quantity. And if you can show that the constants of nature happen to be so that they maximize the number of black holes in the universe, that's predictive. You can calculate something from it. So I find this very intriguing. And David Deutsch is kind of making a similar point when he argues, for example, that the laws of nature have to be so that they can give rise to Turing machines, so to particular types of universal computers. That tells you something about the properties that the laws of nature must have. But it's not a statement about the tiny little particles.
Right. Thank you, Lee. If I could come to you again on this question, and I'm struck in particular by what both you and Sabine have said about how these issues seem to point towards the potential to tell us something about time. So what we're talking about here is not, the laws change over time, but actually that unchanging laws the changing laws or evolving laws might actually give us some insight into what time is in the first place.
Yes, one very important aspect of that, which we worked on with Marina Cortez for a long time, is the question of whether time is reversible. If time is something dynamic, as I mentioned, which creates moments upon moments upon moments, if that's fundamentally what the world is, we posited that it was not reversible. And then we, of course, have a lot to explain because many of the laws on the intermediate scales, like electromagnetism, are reversible. Another thing, to come to your question about multiverses, we found it in the work with Marina very important to assume that there is only one universe. And that has consequences for the ways those systems evolve. And it's a little bit too complicated to explain that here. But I don't know if the postulate of many universes is helpful. I had a version of it as well. But the postulate that there is only one universe seems to me very fruitful.
And a question pops into my mind, Lee, that if laws have evolved and are emergent in this way, is there anything inevitable about that? Could we have ended up evolving different laws just as evolution is contingent?
That's a very, very interesting question, and I certainly don't know enough. And I follow Paul, and also recently my colleagues Marina and Andrew and Stu Kaufman in using biology, not just to fit biology into physics, but as Paul has been doing, and Sarah for some time at your center, to use biology as an example of how we're to think of these kinds of questions.
That's a really interesting perspective, that biology can be useful to physics and not just the other way around. End by thanking the speakers, the panelists. Thank you.
For more debates, talks and interviews, subscribe today to the Institute of Art and Ideas at IAI TV.